Today what we'll do is begin our last topic for the year, stats. So it's a fairly neat way to finish because it actually will combine a bit of binomial and a bit of normal distributions, but it's very different and it became part of the course I think in 2016, so it's relatively recent. Alright, so we need to know about population parameters and sample statistics, okay? Now, what are we doing here? Well, when we are interested in obtaining information from a certain population, it's usually not practical or even possible to survey every single member of the population. Okay, so imagine I said to you guys, listen, I want to know what the feeling is about, I don't know, the canteen at school. Can you please go and survey or ask all the students what their feelings are for this set of questions? I hope you would turn to me and say, I don't think that that's ideal, and perhaps we could get a sample of students which would be faster and much, much more efficient. And I would say, yeah, definitely. Okay. So some situations where this wouldn't be possible, the number of Year 12 students in Australia. Imagine trying to survey all students about their feelings on leaving school or something. I don't know, whatever. Might be hard to access. Okay, so you take, or looking at all sharks in the ocean, so you can't do that. Wouldn't really want to get near sharks either. Quite dangerous, I would say. So hard to access, but also fairly dangerous. I want to kind of be doing that. Or the data collection process may be destructive, so testing all batteries to see how long they would last would mean that there's none left to sell. Like you go, oh yeah, on average batteries seem to last for 3 days, and I tested all of the batteries in the world to ensure this. Well, there's now no batteries left. Okay, so hopefully you see that it's logical to take a sample. And what you want to do is, when you find out something from the sample, you find out what's true for the population. Okay, so we take a smaller sample from the population, and hopefully we can generalize back that piece of information to the population. So a population is a group that you want to know something about, and a sample is the group within the population that you collect the information from. So it's smaller than the population. So the number of members of a sample is called the sample size n. Okay, so we use lower case to represent that. And the population size, we use the uppercase n to represent the number of members in the population. And sometimes we just don't even know what the population size is. Again, if I said to you, the number of sharks in the world, well, how many is there? Wouldn't have a clue. No one sort of sat down and counted. The problem is that they move. So, you count one and you're like, hang on, did I count that one? You then go to a different site and some of them have moved. Anyway, you can see the difficulty with actually sometimes kept trying to state what the population size actually is. So what a parameter is a characteristic of a population. And what a statistic is it's a characteristic of a sample. And that's why this particular unit is known as stats, because what we're doing is we're looking at samples, okay, and then trying to generalize to the population. So we call this stats. This means that a statistic is always known exactly, okay, because we do take the sample. So we know the statistics. What we don't know about often is the population. Okay, so what we do is we generally take the sample and generalize, okay, and in that sense, a parameter is usually estimated from the sample statistic. So we don't really know how true it is, okay, we only estimate the parameter from the sample that we've taken. Okay, so that when we sample, what it's really important that we do is take a representative sample. So again, suppose we were interested in the effect of computer use on the eyesight of uni students, and I can relate to this example. If we went into the lecture theatre and selected all students in the 2 front rows, this would be a problem to talk about computer use on eyesight, because I used to sit really close to the front of the lecture theatre, in the lecture theatre, because I just couldn't see. I had to, that was even with my glasses. So that would be a bad sample. So to take or make valid conclusions about the population from the sample, we'd like the sample to reflect the true characteristics of the population. So we've got to make sure that we take a random sample. Okay, and how to ensure it's random? Each person has an equal chance of being chosen. So what you might do is number each student in the lecture theatre. So you might have student 1, student 2, student 3, student 4, student 5. And then what you would do is take or choose one of these people at random. And again, humans are really bad at doing this. Okay, so if I said to you, choose a random number between 1 and 5, you might choose either 2 or 4. Okay, maybe not the central number. Generally, people don't choose the outside two numbers. So you'd either go 2 or 4 would be my best bet. So again, what we usually use is a computer to do the generating of the random number, because the computer has no kind of bias or logic to it. It just will choose literally the random number. Okay, so what we're going to do is get stuck into the distribution of the sample proportion, and we're going to do this for what we call a small population. Now, what's going to happen with small populations is that they're going to be without replacement. Okay, that's the really important thing. With large populations, we assume replacement when we take a sample. With small populations, we assume without replacement. So if you imagine that there is, I don't know, a small population, we've got 5 students here, okay, and what we want to know is a little bit of information about how these students are feeling about, I don't know, life or something. Okay, when we take a sample of someone, what we do is we grab this person and go, bring them out and go, hey, here's the questions, can you answer them? Okay, and then we take the next person. We don't put that person back into the sample, because then we might get them again. All right, so what we would do is that there would be 5 people first, and then after we've sampled one person, we'd grab another person and ask them their views. Okay, so we would not replace them. Okay, whereas with a large population, imagine we have got a population of, I don't know, let's go 100,000 people. Okay, when I take a sample of someone, all right, we get someone out to ask questions, we still say that there's roughly 100,000 people in the population, because the effects of taking someone out are negligible. All right, so small samples, we're interested in noting that it is without replacement. Okay, so we don't put them back into the sample, whereas with large populations, we assume that they go back into the population. So let's get stuck into this one here, and today we'll only do small populations. In the next lesson, we'll do large, and you'll see the difference between the two. So a bag contains 6 blue balls and 4 red balls. The actual proportion of blue balls in the bag is 6 in 10 or 3 in 5. Okay, so we know this, and this is what we call the population proportion. We denote this with the letter P. So we know what the population proportion is. It's 3 in 5. Often in real life, we don't know this because the sample or the population is just too large to work it out exactly. Okay, but there's only 10 balls here, so we can work it out if there's only 10. All right, if samples of size 3 are taken from the bag without replacement, then the sample could contain either 0, 1, 2, or 3 blue balls, and they would look as follows. So we could get 0 blue balls out of 3 that we take. We could get 1 blue ball out of 3. We could get 2 blue balls out of 3 in the sample, or we could get all 3. Now, if we did that, what are the chances of getting all 3 blue balls? You'd be like, wow, that's amazing. Okay, so what we can do now is we're going to look at the chance of getting each of these samples. Okay, that is, what are the chances of getting no blue balls, 1 blue ball, 2 blue balls, or 3 blue balls. All right, now here's a little bit of notation, and because we've jumped straight to 17b here in these notes, you won't know what on earth this thing here is unless you do spec. So this thing here is called p hat. That's the way we look at that letter. That's called p hat. And what that is, that's the values that a random variable could take. Okay, now a random variable in this case is capital P hat. That's the sample proportion. Okay, and the values it can take on is lowercase p hat. Okay, so the proportion of blue balls in the sample p hat is each of these things here. So p hat could be 0 and 3. It could be 1 in 3. It could be 2 in 3. Or it could be 3 in 3. These are the possible values of what we call the sample proportion. Okay, now what we're going to do is get the probability of each of these happening. Okay, so the only way to do this with a small sample is that we do it using a tree diagram. Okay, so what we are looking at here is the chance of getting, so we can get either blue or, what was it? Blue or red. All right, and blue was 6 in 10. And red was 4 in 10. And I'll leave it on 10 because there's 10 marbles in the bag. All right, then I'm going to take another pick, all right, which is blue or red, 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 blue or red. So this represents the first sampling, this represents the second sample, and this represents the third sample. All right, now if I grab a blue one first, that means there'll be 5 blues left in 9. If I grab a red one next, there's 4 in 9. If I grab a red one first, there'll be 3 in 9. That will mean that there's 6 in 9 for a blue. All right, down here, if I grabbed a blue followed by a blue, there'd be 4 left in 8. I grab a red, we've grabbed none yet, so there's still a 4 in, how many reds are left? 4 in 8 chance. Well, that makes sense as well, because 4 on 8 plus 4 on 8 is 1. Okay, so we've got a blue followed by a red. Now there's 5 blues left in 8. Now because we grabbed a red over here, that means that there's going to be 3 of them out of 8, which is also 8 on 8. Okay, we've got a red followed by a blue followed by another blue. That's 5 in 8. And then a red is going to be 3 in 8. All right, almost there. We've got a red followed by a red followed by a red. That's 2 in 8. That means blue. We haven't grabbed any yet, so there's still 6 in 8. All right, so now let's calculate our probabilities. Now, this probability, 0 blue balls, means basically I've grabbed red, red, red. All right, red, red, red. And again, you might think, ooh, can't we use binomial for this? No, you can't, because they're not independent. It is without replacement. Now again, just a bit of a teaser. When we get to large populations, absolutely we're using binomial, and it's so, so powerful. Anyway, getting ahead of myself, 4 on 10 times 3 on 9 times 4 on 10 times 3 on 9 times 2 on 8. Just bracket that just to make sure. 1 in 30. Okay, now at the other side here, we've got the chance of getting all 3 blues. That's going to be 6 in 10 times 5 in 9 times 4 in 8, 1/6. Okay, 1 blue ball. Okay, so 1 blue ball is going to be blue, red, red. It's going to be red, blue, red, and it's going to be red, red, blue. So this is going to be a bit of a pain to work out. Yeah, you might get a little bit bored, so chuck me on double speed here. So we've got blue, red, red is going to be 6 on 10 times 4 on 9 times, so it's blue, red, red, 3 on 8. That's that one. Okay, red, blue, red is going to be 4 in 10. Red, blue is going to be 6 on 9. And then red is going to be 3 on 8. So red, blue, red. Now what you might notice has happened, 3, 6, 4, 3, 6, 4, 10, 9, 8, 10, 9, 8. So the next one is going to be the same numbers in the numerator and the denominator, albeit a different order. Let's confirm that. Red, 4 in 10. Red is going to be 3 in 9. And blue, 6 in 8. 4, 3, 6, 4, 3, 6, 10, 9, 8, 10, 9, 8. So to do this on the calculator, it's really not that bad. All we'll do is 6 on 10 times 4 on 9 times 3 on 8. Let's work out the answer, and then we're just going to multiply that by 3. So that one is going to be 3 in 10. Now we can do the same thing for blue, blue, red, red, blue, blue, or whatever. But all I'll do is use the rule for probability, which is 1, remove this, remove this, remove this, is going to be our probability. So 1 in 30 plus 3 in 10 plus 1/6 is a half. 1 take away a half is obviously a half. I can't believe I just did that on the calculator. There it is there. All right, so we've got our distribution of the sample, okay? Now, let's just see whether this makes sense. So the highest probability is, so it's a really low probability to get no blue balls, okay? And that should make sense because there's 6 of them in this bag, all right? And so if I didn't draw any blue balls out of the bag, I'd be sort of going, wow, that is really, really unlikely. Okay, in fact, there's a 1 in 30 chance. Whereas 2 blue balls, that's a half, okay? And we know that the proportion, okay, of blue balls, there's more, slightly more, so it's 3/5, okay? So we can see there that 2/3 and 3/5, so 2/3 is 0.66, 3/5 is 0.6, so we can see that that is very, very probable. So again, if we took a sample and you said to me, wow, I can't believe it, we got 2 blue balls out of 3, I'd go, gee, really? I mean, I'd expect that pretty much to happen. Okay, so the possible values of p hat and their associated probabilities together form a probability distribution for a random variable p hat, but this is, again, capital. Okay, so this is, again, familiar to us maybe because we use capital X to represent the values, the random variable, and then lowercase to look at the values it can take on, okay? So the probabilities are here. Let's write them down again. So p hat could take the value 0 out of 3. That's one possible sample. 1 out of 3, 2 out of 3, and 3 out of 3. Okay? And what were the probabilities? 1 in 30, 3 in 10, 3 in 10, it was a half. Can't remember the other one. 1/6. So these are the values that or the probabilities that the random variable can take on. So this basically, the way to read this is, what are the chances of this happening? What is the probability that the random variable takes this possible value, 0 out of 3? It's 1 in 30. What are the chances that we get 1 in 3? That's a 3 in 10 chance, etc., etc. So the distribution of a statistic which is calculated from a sample is called the sample distribution. Okay, so this is the sample distribution. Okay, so use the sampling distribution above to determine the probability that the proportion of blue balls in the sample size of 3 is more than 0.5. So we want to see the chance of p hat being greater than a quarter, basically. All right, so a quarter is 0.25, a third is 0.3 recurring. So it's these values here. So what we're looking at is 3 in 10 plus a half plus a sixth. Okay, that's going to not be 1 in 30, so it's going to be 29 on 30. Okay, find the probability that the random variable takes on a value larger than a half, given that we know the sample proportion is greater than a quarter. So this is just a classic conditional problem, and this is a subset of this. So we're good to go. So we're just going to work out the probability that p hat is greater than a half over the probability that p hat is greater than a quarter. Okay, so greater than a half is going to be, well, a half is 0.5, so it's these two added together. So we've got 3 on 6 plus 1 on 6 is 4 on 6. So that one there is 4 on 6. And what we're going to do is divide that by greater than a quarter, which is 29 on 30. Okay. 5, 20 on 29. That's the chances of this particular thing. All right, so hopefully that has been a relatively gentle introduction. All right. These are the questions that you need to complete. Good luck.